Hi everyone, in this session we will learn about building a data frame using molecular descriptors. This presentation is largely based on information provided on the homepage of the Fall 2019 Cheminfomatics Online Learning and Collaborating Center course. For further details, you can visit the course homepage shown at the bottom of the slide. Since our previous session, we have focused on how to work with chemical information. I mentioned that we would gradually demonstrate how chemical information calculated or derived using Python's RDKit library can be utilized or correlated to predict properties such as the boiling point of a compound. Now that we have a clearer sense of a direction, I would like to present two plots for discussion. Let's ask ourselves an important question: which of these two plots better illustrates the trend? The plot on the left may suggest a linear trend, but there is a significant uncertainty about what happens in the middle region of the plot. In contrast, the plot on the right exhibits some variability, clearly highlights the linear trend. Therefore, the plot on the right appears to be more effective in showing the trend and might even be suitable for predictive purposes. So, what accounts for the difference? The most obvious distinction is that the plot on the right includes more data points than the one on the left. This highlights an essential insight. The number of data points plays a critical role in understanding trends and making reliable predictions. In the previous session, we explored the elegance of coding in performing repetitive calculations. The code demonstrated its capability to calculate the two-dimensional molecular descriptors for 5 molecules just as efficiently as it would for a single molecule. In this session, building on the for-loop structure introduced earlier, we will learn how to leverage it further to compute a large number of two-dimensional molecular descriptors using a data frame containing extensive data. Now we know that having a large number of data points is crucial for understanding trends and making predictions. But how can we efficiently gather a large number of data? Entering data manually one by one is too time-consuming. A better approach is to allow the computer to read from a data input file containing many values. This code shows how to do that. Let's analyze the code. The first line states, import pandas with the alias or shortened name PD. This creates a pandas library instance, granting access to its extensive features and functions. Pandas, along with NumPy, is one of the most popular library in the Python ecosystem. It offers powerful tools for working with arrays and performing numerical computations. One of its functions, read_CSV, is used to read input data from a CSV comma-separated value file. So the second line reads the file bp.csv and loads this data into a data frame named df. In one of my YouTube sessions, Python Programming for Chemists, A brief overview. I explained that a data frame is similar to an Excel spreadsheet, but tailored for Python's ecosystem. The third line specifies print the contents of the data frame, which has been built from the input file bp.csv. The output is displayed below. This database represents a collection of molecules and their properties, where each row corresponds to a unique record and each column represents a specific feature. For each molecule, the database provides the compound number, the name, the boiling point in degrees Celsius, the boiling point in degree Kelvin, molecular structure in SMILES notation, and the molecular weight. We have just confirmed that the data input has been successfully read and we have built a data frame from it. However, we have a challenge. We cannot directly link the boiling point to the SMILES strings. What we need is a bridge, specifically one-dimensional or two-dimensional molecular descriptors to establish meaningful correlations. To achieve this, we need to calculate these molecular descriptors that we have studied before and append them to the existing data frame created from the bp.csv input file. So to visualize our goal, here is the output we're aiming for. We have table of information, but we also have descriptors added to the data frame. So immediately after the molecular weight column, we will add winner index column, Zagreb index 1 column, Zagreb index 2 column. Now that we have visualized what needs to be done to the data frame, in the next slide we will write the script to make this happen. In our previous sessions, we learned several key skills calculating the winner index and Zagreb index 1 and Zagreb index 2, reading data from input files, and building for loop structures to automate calculations. Now we are going to bring all of that knowledge together to calculate molecular descriptors and add them to our existing data frame. Here is how we will proceed step by step. First, importing required modules. To convert SMILES strings into the molecule object data format, we import RDKit's chem module. For the winner index calculation, we use Modred's winner index module. Similarly, for Zagreb index calculations, we use Modred's Zagreb index module. And for the building and manipulating the data frame, we import the pandas library. Now, creating descriptor instances. We create descriptor instances for the winner index and Zagreb index 1 and Zagreb index 2. These instances make it easier to compute these indices with simpler code later on. Reading the input file. As we did in the 2 slides ago, we read data from the file bp.csv and load it into a data frame df. Initializing empty list. We prepare empty list or one-dimensional array to to store molecular descriptors for each molecule. Previously, I explained that an array is similar to a variable, but instead of storing a single element, it can hold multiple elements. To the empty one-dimensional arrays, result underscore winner, result underscore z1, result underscore z2. Winner index, Zagreb index 1 and Zagreb index 2 of each molecule in the data frame will be added one by one in the later part of the code. Now, building the for loop part, we use the iter_row function to iterate through each row of the data frame. This loop structure allows us to calculate molecular descriptors for each molecule. For each iteration, it takes index of the row and the contents of the row. Now, performing the repeated calculation within the loop, see the indented line of the code. This is the part that are going to be repeated within this for loop. Here we extract the smile strings from the current row by selecting the value in the smiles column. Notice how we access the column value using square brackets and the column name within quotation marks. And here the column name is smiles. Then we convert smile strings of the molecule to the molecule object format and store the value in the variable molecule. And this value is going to be repeatedly used to calculate winner index, Zagreb index 1 and Zagreb index 2. What is different in this code, in these lines of code, is that we're appending these values to this initially empty set, result underscore winner. So after calculating the winner index, the resulting value is going to be added to this array result underscore winner. Similarly, for Zagreb index 1, once the value is calculated, we're going to add it to this array called result underscore z1. And similarly, we do the same thing for Zagreb index 2. So for each iteration, it's going to calculate one winner index, one Zagreb index 1, and one Zagreb index 2. These are going to be added to this array result underscore winner, result underscore z1, result underscore z2. Now, appending new columns to the data frame and saving the data. Whatever is stored in this array called result underscore winner, result underscore z1, result underscore z2 is going to be added to the data frame as a new column with this heading, new column with this heading, and new column with this heading. So in other words, we add the calculated descriptor list as a new columns in the data frame and save it as a CSV file with this function to_CSV. Finally, we print out the data frame. Sometimes when we get too absorbed in the details of the code, we can lose sight of the broader picture, the flow of the processes within the code. In such situation, visualizing the flow through a diagram can be extremely helpful. Flow diagrams use distinct shapes to represent different types of processes. Let me quickly walk you through some common shapes and their meanings. Basically, this is the same code that we just discussed. It is just represented in a different way in this flow diagram. This oval shapes represents the start or end of the process. It typically contains the term like start or end. Start or end. The rectangle represents a specific process or action step in the flow, such as a function, operation, or task. It will usually describe what's happening at that stage. Parallelogram is for input or output. This shape is used to indicate input or output operations, like reading data from a file, or displaying output, or accepting user input. The diamond shape indicates a decision point in the flow where the path branches based on a condition. For example, an if-else or switch statement. Inside the diamond, you will find a question with the branches typically labeled as yes or no, or sometimes true or false. Arrows show the direction of the flow between the shapes, indicating the sequence of operations. Now let's quickly go through the code flow. First, the necessary modules are imported. Then instances of required functions are created. In our case, winner index, Zagreb index 1 and Zagreb index 2. Then data is read from a file. In our case, we read the file from bp.csv. New empty arrays are initialized for use in the process. Those three arrays starts with results underscore. The code then proceeds with a for loop, repeating the task of calculation and appending indices to the arrays. Once the loop completes, new columns are added to the data frame, and the final data frame is printed. This process flow diagram can help us better understand the overall structure and the order of operations, providing a clear overview of how the code executes. The output of the code that we have seen in the previous slide looks like this. As you can see, the last three columns display the newly added descriptors to the data frame. Let's run the same code in the Visual Studio Code Editor. Before we execute the code, I would like to point out that I have added one additional print statement to show you the initial state of the data frame before any modification, right after reading the file. Let's run the code by clicking the play button. As a result of the code execution, we see two data frames or tables. 1, 2. The first table shows the original data frame without 3 indices. The second table includes winner index column, Zagreb index 1 column, Zagreb index 2 columns. These clearly demonstrate that the indices were successfully appended to the data frame. We have successfully calculated 3 molecular descriptors for each molecule and expanded the data frame to include this new information. Now we need to visualize the data to check for any potential correlations. To do this, we will plot single variable responses against the boiling point using Python. Let's take a closer look at the code. First, we import the plotting module matplotlib.pyplot and assign it the shortened name PLT. This creates the PLT class instance, which provides all the features and functions required for plotting. The second line specifies that we are plotting the winner index from the data frame against the boiling point in Kelvin. Data for x-axis, data for y-axis. Scatter function for plotting, scatter plot. The third line labels the x-axis as winner index. The fourth line labels the y-axis as boiling point in Kelvin. The fifth line displays the scatter plot. The resulting plot will look like this. The winner index appears to have a correlation resembling a square root function. Similarly, we can write similar codes to plot the molecular weight Zagreb index 1, Zagreb index 2 against the boiling point. We just need to change the second and third line of the code a little bit for each descriptors. These additional plots reveal mostly linear relationships with the boiling point. There are a couple of interesting points. First, 4 descriptors all show correlation. Second, the responses for Zagreb index 1, Zagreb index 2 are very similar, suggesting potential collinearity between these two descriptors. Collinearity means that they contain similar or redundant information. This is the end of the session. We're about halfway to building the prediction model for the boiling point based on the QSPR principle. Thank you for your attention. I hope you found the session engaging and informative.